Have you ever looked up at the night sky and wondered, where did it all begin? How did billions of stars, billions of galaxies, and us come into existence? For thousands of years, people have searched for answers in mythology, philosophy, and now science has revealed an astonishing picture, the Big Bang Theory. Let's turn back the clock to a time when space, time, and everything we know was just a tiny, incredibly hot, dense point. Get ready to explore the origins of our universe. Don't forget to subscribe to the channel so you don't miss out on other exciting space exploration videos. If you find the video interesting and useful, please like and share to support us. Welcome to the great journey of space exploration. Today, we will explore one of the most profound and controversial scientific theories of all time, the Big Bang Theory. It is not just a story of the beginning, but also a symphony of physics, mathematics, and amazing discoveries that have completely changed the way we see ourselves and our place in the universe. Let's start with a basic truth that we all know. The universe is expanding. This is not a hypothesis, but an actual observation proven by the work of the great astronomer Edwin Hubble in the 1920s. Hubble discovered that most galaxies are moving away from us, and the farther away they are, the faster they are moving. This phenomenon, called a redshift in the spectrum of light from galaxies, is like a train whistle changing pitch as it passes you. This can only happen if the space between galaxies is expanding, carrying them further away. If the universe is expanding, then if we go back in time, everything should be closer together. Continuing to go back in time, we will reach a point where all the matter and energy of the universe is compressed into an infinitesimally small, incredibly hot, dense volume. This is the core idea of the Big Bang. Imagine a balloon with ink dots on the surface. When you inflate the balloon, the ink dots don't move across the surface. The surface expands and carries the ink dots away from each other. Our universe is similar. There is no center of the explosion. Every point is expanding away from every other point. So what other evidence supports the Big Bang Theory besides the expansion of the universe? One of the strongest is the existence of the cosmic microwave background, or CMB. In 1964, two scientists, Arno Penzias and Robert Wilson, while trying to eliminate a mysterious noise in their antenna, accidentally discovered a constant noise signal throughout the sky. It turned out to be the leftover echo of the Big Bang, the heat radiation left over from the very first moments of the universe. When the universe was very young, it was extremely hot and dense, filled with a plasma soup of elementary particles and photons. Photons could not move freely and were constantly colliding with charged particles. About 380,000 years after the Big Bang, when the universe expanded and cooled enough, electrons and protons combined to form neutral hydrogen atoms. At this point, photons were no longer trapped and could move freely through space. This radiation, after billions of years of expansion with the universe, has cooled significantly, from thousands of degrees Kelvin to about 2.7 Kelvin, corresponding to microwave wavelengths. The CMB is a direct picture of the early universe, telling us how homogeneous it was and how small fluctuations in temperature later became the seeds for the formation of galaxies. The third piece of evidence comes from the abundance of light elements in the universe. Scientists have calculated that in the first few minutes after the Big Bang, when the universe was still hot and dense enough, nuclear fusion occurred, creating most of the hydrogen, 75%, and helium, 25%, atoms we see today, along with small amounts of lithium and beryllium. This ratio matches remarkably well with what we observe in the universe, providing another strong case for the Big Bang model. Now, let's go back in time and travel through the first moments of the universe from an incredibly hot and dense singularity. We begin with the Planck Epoch, about 10 to the negative 43 seconds after the Big Bang. This is when the universe was so small, hot, and dense that our current laws of physics no longer apply. The four fundamental forces of nature, gravity, electromagnetism, strong nuclear force, and weak nuclear force, were thought to have unified into a single superforce. To understand this period, we need a quantum theory of gravity, which we do not yet have. Then came the inflationary epoch, which lasted from about 10 to the negative 36 to 10 to the negative 32 seconds. This was a period of extremely rapid and exponential expansion of space. In a very brief moment, the universe expanded at a speed far exceeding the speed of light, swelling from a size smaller than an atom to the size of a bowling ball. Inflation solves some of the major problems of the standard Big Bang model, such as the flatness problem and the horizon problem, explaining why the universe is uniform and has the large structure we observe. After inflation ended, the universe continued to expand but at a slower rate and began to cool. The enormous energy of inflation was converted into a dense soup of elementary particles, quarks, electrons, neutrinos, and their antiparticles. This was the quark epoch and lepton epoch. The temperature remained incredibly high, allowing particle-antiparticle pairs to be created and annihilated continuously. However, there is a small but important imbalance. For every billion or so particle-antiparticle pairs, there is one extra particle of matter that has no antiparticle to annihilate. This tiny imbalance is the miracle that allows matter to exist. Without it, the universe would just be a sea of photons and pure energy.
When the universe cooled enough, about 10 to the minus 6 seconds, quarks began to combine to form protons and neutrons. This was the hadron epoch. These protons and neutrons were the first building blocks of atomic nuclei. About 1 second after the Big Bang, the universe had cooled to about 10 billion degrees Kelvin, still hundreds of times hotter than the core of the Sun. At this point, neutrinos separated from the rest of the universe, moving freely and forming the cosmic neutrino background, similar to the CMB, but much harder to detect. Between a few minutes and about 20 minutes after the Big Bang, the universe entered the Big Bang nucleosynthesis, or BBN. The temperature and density of the universe allowed protons and neutrons to combine to form the nuclei of helium-4, deuterium, heavy hydrogen, helium-3, and a small amount of lithium-7. All heavier elements were created later in the hearts of stars. The success of BBN in predicting the proportions of lighter elements is one of the greatest milestones of the Big Bang model. After 20 minutes, the universe continued to expand and cool, but was still too hot for electrons to combine with nuclei to form neutral atoms. The universe remained an opaque ionized plasma where light could not penetrate. This period lasted about 380,000 years. About 380,000 years after the Big Bang, when the temperature dropped to about 3,000 degrees Kelvin, electrons were finally able to stick to nuclei to form neutral atoms, mostly hydrogen and helium. This was the recombination and decoupling event. The universe became transparent to radiation, and photons were finally able to move freely. These photons are the cosmic microwave background that Penzias and Wilson discovered. We often call the next period the Dark Ages, which lasted from about 380,000 years to a few hundred million years after the Big Bang. During this period, the universe was filled with neutral atoms, with no stars or galaxies forming to emit light. There was no light source other than the cooled CMB radiation and 21-centimeter photons from primordial hydrogen gas. Despite its name, this was a crucial phase, setting the stage for the formation of the first structures in the universe. Finally, a few 100 million years after the Big Bang, gravity began to exert its influence on slightly higher density regions of the early universe. The giant gas clouds gradually collapsed, compressing the material, and under the immense pressure and temperature, the first stars were lit. This was the reionization event that ended the Dark Ages. These stars, much larger and brighter than our Sun, synthesized heavier elements such as carbon, oxygen, and iron through nuclear fusion reactions in their cores. When they died in spectacular supernova explosions, they scattered these elements into space, creating the materials for the next generation of stars, planets, and eventually life. Since then, the universe has continued to expand, cool, and develop the complex structures such as the galaxies, galaxy clusters, and superclusters we observe. This entire process, spanning 13.8 billion years, from a singularity to the vast, life-filled universe we know today, is an astonishing story of formation, evolution, and increasing complexity. The Big Bang Theory is not an explosion in the conventional sense, not a bomb exploding in empty space. It is the expansion of space itself, carrying all the matter and energy within it. It does not answer the question of what was before the Big Bang, or where did the Big Bang happen, because it describes the very beginning of space and time. This gives a sense of utter humility and wonder. It shows us, tiny creatures on a small blue planet, living in a universe that has undergone an extraordinary journey to get here. The temperature of the universe in its first moments was unimaginable. Even when protons and neutrons formed, it was still trillions of degrees Kelvin. Only after a few 100,000 years did it cool enough for neutral atoms to form. This cooling is the key factor that allows matter to form and then reassemble under the influence of gravity. If there is anything the Big Bang Theory teaches us, it is that the universe is not static. It is dynamic, ever-changing, and ever-evolving. And we are an inseparable part of it, created from the same stardust that witnessed the greatest event in the history of the universe. It's a lesson in connection, in common origin, and in a future still to be discovered. The Big Bang Theory has opened the door to understanding the origins of the universe. But what about its future? Will the universe continue to expand forever, or will it collapse in a big crunch? What will happen to all the matter and energy as space continues to expand? Stay tuned for our next video where we will explore the fate of the universe, inflation, and the possibility of cosmic collapse, to unravel the mysteries of this grand finale. Don't forget to like, share, and subscribe to our channel so you don't miss out on other exciting scientific discoveries.